Hello, Jawad.
Hi, Sam, how are you?
I am good. How are you doing?
So, these meetings are recorded.
I see.
The recording then gets available to the uh, community.
Mm-hmm.
So, I suggest when you start talking, then you turn on your video.
Turn off or turn on?
Turn on if you like. It's actually a good idea to turn it on during,
Oh, okay. Okay. Okay.
but sound
Gotcha.
check and all of that looks good. So I
Oh,
will go through, I'll open the meeting, couple of housekeeping items, then I'll introduce you, and then you can go through the.
thank you. So, does this mean also that the presentation itself becomes available or no? Just the
Yes.
recording?
Well, it's up to you. If you give me presentation, I'll make it available.
I see. No, I think the recording is good enough, I think, for now, but thank you. I need to educate myself on the subgroups and
Sure.
Morning all. Hey, quick
Hey,
question
Alan.
for you, Sam. Hyperion, I always thought they were an analyst company.
Oh no, we are not. We are not an analyst company. We aspire to be a manufacturer here in the US.
Right. Yeah, no, I guess I did take a closer look, but is there I'm pretty sure there's a high performance compute analysis analyst company called Hyperion as well.
Oh wow, well, there is a lot of
Maybe that's
Hyperions.
me. Maybe I
Well,
got it wrong.
we have a lot of brethren, I guess, but we have no association with that entity. No.
Yeah, Hyperion Research, spelled exactly the same,
Ah, okay.
with a blue H.
Oh,
Take a look at them.
okay. I will. Thank you.
Welcome, everyone. We'll just wait maybe another minute or so for people to join. Okay, I think we probably will get going. Let me just quickly share. So thank you so much for joining the meeting today. Our main agenda item today is a talk by Dr. Sam Salama, and the talk is related to various aspects of 3D integration and advanced packaging. Sam is the CEO of Hyperion Technologies. Before then, Sam was a GM at Intel, was responsible for their high volume manufacturing and global assembly and packaging supply chain. And I had brief overlap with Sam at Intel, and Sam was one of the early guys who had developed and productized Intel's EMIB technology. And if you look at his academic background, is really impressive. He's right now on several boards of companies, and his own company, Hyperion, is doing pretty notable work. So he gave a talk at Chiplet Summit. That was a keynote, and I requested that if he could give us maybe a slightly expanded version of it and answer some of the questions, that would help a lot, because most of the group here comes from the design background, so it's good for us to know a little bit on the manufacturing side of things. So before I hand it over to Sam, there are a few things related to the organization that I want to mention. So first, we're going to welcome Anu Ramamurthy to join me as the co-lead of ODSA, and there will be some announcements to that effect coming up soon. Next week, I'm planning to basically work with Anu, and we'll just in the same meeting talk a little bit more about the organizational topics. And then on March 15th and March 22nd, we have a business workshop, which will basically be happening at the same time, same Zoom link. And it will start at 8 a.m. on Friday. And Merrick has put together a pretty awesome list of speakers for that. In April, we do have a slot marked for Mike Bartley to talk about die-to-die PHY-test white paper. They are looking for fellow travelers. So in the month of March, we have a DVCon, Design Verification Conference, coming up in San Jose, and then there is NVIDIA GTC that is in high demand at the moment. So before I hand it over to Sam, are there any questions? Anybody wants to talk about anything related to organization or logistics?
Very excited about Sam's talk today. I just brought up something last week on having a central bunch of wire glossary. Just want to make sure it is on our list of agenda to revisit at some point.
Okay, Halia, so let me just write that down. I think I missed that. Bunch of wire glows repo, right?
Yes, yep.
That's,
thank you.
So this is the request. Okay.
Yeah, we should bring up the BOW meeting on that one day. Yeah.
Okay, so James, you're gonna take that action, right?
Yeah.
Okay. Okay, Sam, it's all yours.
Okay, thank you very much, Jawad. Good morning, everyone. Really delighted to be here. I always admired the work that you guys are doing in the OCB different groups and subgroups, and I'm really delighted to be invited, and I look forward to having a very productive discussion today. My background, as Jawad mentioned, is fabrication, manufacturing, and materials engineering. So always enjoy learning from design experts and architects like most of the people who are here. So let me share my screen, and then we can get started. Okay, and I don't know if, can everybody see my screen?
Yes.
Okay, great, thank you. All right, so Jawad asked me to bring a version of the talk I gave at the Chiplet Summits a few weeks ago. So as I said, very delighted to be here, and I am going to talk about sharing my perspective on advanced packaging, specifically in the era of chiplets. We'll talk about what role that advanced packaging play today, what role it needs to play in the future, what is missing. We'll also take a look on the supply chain, how it's architected today, and what needs to change. If we have time at the end, I will take this opportunity to also share some insights into the work that we're doing here at Hyperion. We're working on introducing a new process and architecture specifically designed for AI and high-performance computing applications. Okay, so with that in mind, this is my first slide. I think this particular crowd is very familiar with this. You guys do a lot of work related to design and architecture, so you understand the cadence of the process technology scaling. And if we just take a historical look, I'm not going to delve into the details of each one of the waves that drove our industry growth from a market perspective, but I think it's important to reflect on a very interesting distinction between what's going on in the current wave that is upon us, focusing mostly on ambient computing and generative AI, and compare it to the previous waves that drove the growth in the industry. And from my perspective, I think the distinction is mainly related to how the device and the application that are associated with this current wave that's upon us is tied to the integrated circuit fabrication technology. If you look at what happened in wave 1, 2, 3, and 4, there was a very close tie between the integrated circuit scaling and the process node at the monolithic die and transistor level, and the nature and the capability of the devices that are being used for each one of those waves. In the current wave that we are in, performance tended to be defined not necessarily by the specificity of the technology node that are being used to fabricate the transistor, but performance used to be defined or seems to be defined by the system level integration. So that particular distinction between the wave that we are in and the previous one seems to also nucleate a very strong paradigm shift in compute. And this slide intended to sort of highlight some of the trends that are coming along with this particular paradigm shift that I am referring to. So most of the devices in the ambient computing and AI application tended to be compute heavy, data intense, and very sensitive to latency. So there is a goal to really shift the whole hierarchy of the network from bringing data to compute that used to be the focus of the previous waves to bringing compute to data for obvious reasons. The other trend that is obvious and also accelerating is the increase in die size and packaging size. On the die size front, if you look at the chart here in the middle of the slide, that's quite obvious, and a lot of people are paying a lot of attention to that because there is obviously a physical limit of how many transistors you can put on a piece of silicon as it relates to the lattice parameter and the atomic structure of the silicon itself. But there is also a physical limit as of how big you can have this monolithic die related to the size of the reticle that you are using for the lithography process. Packaging happens to also see a similar trend, but for other reasons. If you look at the figure of merit of packaging, it's a very simple function that reflects the XY size and also the layer count, how many layers you will build of this particular package. And if you look at the data that I'm summarizing here on the small little table on the right-hand side, the trend of increasing that form factor function for advanced packaging have been very interesting. Continue to increase, but the rate of increase in the last 3 years or so have been significantly higher than the rate of increase in the previous 15 years. And there are multiple reasons for this. There is obviously the heterogeneous integration for chiplets, like we'll talk about, but there is also the associated complexity that comes in manufacturing something like this and coming out with a reasonable yield that can make it affordable. And we'll touch upon this in the subsequent slides. So I think these are some of the trends that, from a manufacturing perspective, are becoming persistent today due to that wave with focus on AI and high-performance computing. The timing of that paradigm shift is interesting because it's also overlapping with the notable deceleration in Moore's law scaling, right? So we are all familiar with what's happening with the rate of scaling according to Moore's law. And if you take a fab-centric view of how would you address that, then the chart that I borrowed from my friend Jawad here would summarize that, okay, taking a fab view of this, I'm going to take a very large monolithic die, I'm going to chop it up into different smaller chiplets. I'm going to address the yield concern and the complexity of fabricating such a die on an advanced node. I think that is great, and it's a trend that started and will continue. However, in my opinion, this is just half of the solution, because it makes an implicit assumption that the reaggregation of these chiplets on the package will continue to scale and will deliver the intended performance requirement from a design perspective. And that's not necessarily the case today. So in order for that particular solution of chiplet integration to continue to scale and maintain the cadence of system level scaling, advanced packaging need to play a bigger role than what it is today. However, despite the fact that there is a difference in scaling rate between advanced packaging and integrated circuit at the device level, that whole trend of chipletization and heterogeneous integration of different chiplets, you can already see that today, especially if you take a look on high-performance computing devices. It's almost exclusive that all these devices are coming out with heterogeneously integrated chips or chiplets on an advanced packaging architecture of some sort. And that trend highlights two things, right? It highlights the fact that chiplet is truly important and critical for continuing Moore's law system level scaling. But it also highlights the fact that packaging and substrate in particular are foundational in offering the interconnect fabric that reaggregates these chiplets on the packaging device and deliver the required system performance. So what does this mean for packaging? I tried to summarize that answer in the little insert on the right-hand side, but I think we probably going to be useful for us to spend some time and talk about what does this mean. So because of what's happening with chipletization and heterogeneous integration, packaging is really shifting. It's moving from a performance enabler and performance preservation to more toward a performance enhancement. And there are different things that I think exemplify that redefined role for advanced packaging. And I tried to summarize that in this particular slide. So packaging need to shift now from focusing on a single or a multi-chip packaging to a heterogeneous integration of a chip, right? This means that the interconnect fabric that is being offered on a substrate or an interposer or an advanced packaging device is becoming an integral part of the circuit design. The second piece is miniaturization. And miniaturization means that you need to have fine feature, like tighter bump pitch, tighter first level of interconnect at the chiplet level, finer trace and space, smaller via, and the dimension of these critical features on the substrates and the interposer are now approaching the same dimensions of the back end of the chip itself. also need to deliver a shorter die-to-die spacing, a more complex power delivery network, come up with material sets and design rule tolerance to deliver high-frequency operation with low loss, and offer thermal management that is inherently built in the packaging device itself. Most of the solutions that are available today in the market would require an active thermal management approach that is not built inside the packaging device, and we'll talk about this. The other thing that package needs to deliver is a larger form factor and a higher layer count that is not necessarily driven by the fact that we just have a more complex and a very tight technology nodes that are being used at the 7 nanometer or the 5 nanometer. But it's also because there is more manufacturing capacity that needs to be delivered, right? So there is warpage management that needs to happen. There is yield of the manufacturing operation that needs to be addressed. And that is really giving a lot of increased complexity to the process of fabricating these packaging device. And simplification with a specific focus on yield and affordability is a big area for packaging to pay attention to. The final and last piece here is redefinition of the supply chain. Today, as I will explain, the supply chain have a specific order into it. Most of the packaging gets done in Asia for some reasons that we will talk about. And the supply chain seems to be over-optimized for cost, but not necessarily from a resilience and robustness and time to market perspective. So those are, in my opinion, things that needs to be co-optimized in order for packaging to step up and deliver the elevated role that is intended for it in the future, specifically with heterogeneous integration. So if we talk about what is the state of the packaging and the substrate scaling, I like to use this chart because it does offer several insights into what's going on. So this chart takes a look over time at the rate of scaling, comparing the integrated circuit or the CMOS technology node scaling rate with the packaging and the substrate and the board scaling rate. So this particular chart is doing that by looking at the critical dimension at the transistor level and also at the substrate level. And when you look at that, few things comes out of that particular chart. You can clearly see that the monolithic scaling on the integrated circuit side is exponentially higher than the packaging rate of scaling, right? That scaling gap is too wide, in my opinion, to be closed just at one specific level of the interconnect hierarchy, whether it's the first level of the interconnect at the interposer or that on the substrate. The gap is too wide, and I believe to be able to effectively close the gap, you need to do this at all different levels in the interconnect hierarchy with some sort of intentional co-optimization. The other thing is, if you overlay the differential rate of scaling between packaging substrate, CMOS, and you look at what's happening to the monolithic die size trend, we are almost approaching the limit here very soon. Now, the fact that we are going to have that limit approached very soon, and the fact that this gap continues to be very wide, highlight the urgency that is needed from an advanced packaging perspective to accelerate the closure of addressing this gap. And obviously, doing that in a manner that pays a lot of attention to design for manufacturing is key, so that we can continue the economics of scaling trend that started at the monolithic level with Moore's law, but continue to do that also effectively at the system level. If we take a look at the state of the supply chain for advanced packaging, I think it's well recognized in the industry that packaging is being concentrated in Asia with the belief that it's being done mostly in Asia because of cost reasons. I think that particular notion is somewhat accurate when you talk about assembly and test. But when you talk about 3D integration through an advanced interposer, or you talk about high-density interconnect substrates, I think there are more serious reasons than just cost. And if I take an example on the high-density interconnect substrate, for instance, there isn't any capability to do that today at the leading edge design rule or at any meaningful high volume manufacturing capacity. So the US contribution of that is zero. One could think that because the perception is packaging is done in Asia to reduce cost, that this high density interconnect will come from a lower cost GPU. Matter of fact is high density interconnect substrates are mostly coming from Japan, with some coming from Taiwan and South Korea. And if you really look at these particular countries, they are not necessarily cheaper to manufacture than the US anymore, right? With specifically Japan, right? So I think there are other reasons why these high density interconnect substrates are there. And I think the reasons are the know-how is there. It's something that started there. And more importantly, the ecosystem, the list of material suppliers, chemical provider, equipment manufacturer that support this particular industry are highly concentrated in Asia, like I'm showing in this bottom chart. So the result of this particular situation is a very interesting fact, right? Most of the wafers that gets fabricated in the US has to fly all the way to Asia, where they get assembled and tested. But the high density interconnect substrates comes from Japan to these other Southeast Asian country. They never touch here in the US. We don't know how they are made. We don't know what it takes to make them. All the details are contained within specific regions. And they get mated with the die, they get assembled and tested, and then they get shipped back globally. So, as I said earlier,
Sam, question. This is a surprise, I guess. So, was there ever a time that substrates were being manufactured in United States and then were shipped out?
That's a really interesting question, Jawad. So, printed circuit board started in the US, assembly started in the US, and there was a time where the printed circuit board would use organic material, but the high density interconnect substrates were made of ceramics. And at that time, there was some capability to do this, especially in the Northeast, right? Like Fishkill and Endicott, and these were part of the captive capability that IBM had at that particular time. However, IBM at that time was focusing on mainframes and very large computing devices that required the usage of the ceramic-based technology. The industry in Japan recognized that scalability on that technology is limited. And back in the late 80s, I think early 90s, the Japanese led the world in making the transition into what is known today as high-density interconnect substrate. So these are the multi-layer laminates that are built on the Ajinomoto material and uses laser to create the vertical interconnect and so forth.
So it's fair to say it was kind of indigenously developed in Japan.
Yes, the organic high-density interconnect substrates as we see it today. That's a fair statement.
Why does nobody talk about this fact? This is illuminating.
Yeah, and actually, I think the interesting part is in order for us to address that piece, I think we have to learn what is being done now and then take that as a fundamental platform over which we can improve. I don't think it's realistic for us to believe that we can circumvent the innovation and the ecosystem that was built in Japan over the last 30 years or so and do something very different that can obviate that quickly. I mean, it's something that needs to be addressed over time, but it's something that is extremely important. However, I would have to tell you that manufacturing is one thing, but the ecosystem that feeds that manufacturing is another thing. I don't believe that it's realistic to expect that you will be able to duplicate that ecosystem very easily. I think collaboration with friendly countries like Japan is extremely important to continue, but there has to be mutual benefit, right? So there has to be value add that both sides continue to feel in order for this to be changed.
Thank you.
Of course. You know, and one other thing I want to say is toward the vision of what we discussed in answering Jawad's question, I think it's also important to recognize that having R&D alone is not sufficient. The reason why there is a dominance of offering these high-density interconnect out of Japan and Taiwan is because a complete ecosystem exists. So high-volume manufacturing, in addition to R&D, are equally important component to strengthen and redefine that particular ecosystem. So with all that we talked about, there are a few observations that I would like to share with the team as of what's going on in the advanced packaging and how it relates to the overall system scaling and the integrated circuit scaling as well. So clearly obvious that advanced packaging role is evolving, right? And with that, there is a noticeable market growth in advanced packaging as well. But market growth, as I will show in a subsequent slide, can be detected in two things. It can be detected by how many units are the demand profile carrying over the years, but also how does this demand increase look like? Usually there is a cyclicality in the semiconductor industry, but if you look at the forecast for majority of the leading advanced packaging solution, you will not really notice that level of cyclicality as obviously as you would when you track equipment for front end or chip demand for front end. And there are some reasons for that that we'll touch upon. The last thing I would like to highlight as an observation is over the years, advanced packaging tended to be looked at as an afterthought, right? So architects and very smart designers will trackly or closely track the integrated circuit scaling, and then they will design their feature into the chips, taking advantage of that economy of scale that's offered by Moore's law, and then they will throw it over the fence, and the advanced packaging guys will be able to wire bond or test that and make it work. There has not really been a lot of co-optimization and a lot of coordination in at least in the roadmap, right? And recently that has been changing, and this is really very positive. Now there is a very tight alignment between how the roadmap looks like on the front end and how does it look like on the back end. And I think that's a very welcome change in how people think about the overall system. But obviously, as we talked before, when you compare the value of these numbers on what's happening in the packaging and what's happening on the front end, there is a wide gap that needs to be bridged at one point. This is a look at the different forecasts that are available today from different outfits, talking about how does advanced packaging CAGR looks like. And depending on where we get our numbers, there is some level of discrepancy. But I think a few things are worth noting here. Number one is when you compare the CAGR of different sub-segments in the overall semi, you will see that advanced packaging is the fastest growing segment. We talked about usually there is cyclicality that gets reflected in die demand and front-end equipment and all that. And advanced packaging, specifically due to the fact that they are becoming more complex, they are becoming larger. So capacity required to fabricate them, even if the unit demand is constant or declining, the capacity that is required to fabricate them is increasing. And as a result, the revenue that's being generated in this particular subsegment will continue to increase monolithically for the next decade or so. Within advanced packaging, the largest or the fastest growing subsegments are two specific ones. One is the high density interconnect substrates, and then the other one is the 2.5D and the 3D integration of chiplets, whether it's an RDL on an interposer or other architectures that are being looked at. And we'll talk about some of these architectures in the subsequent slides as well. So how is the technology, or how is the industry addressing this packaging scaling requirement so that they can take advantage of the anticipated or the persistent CAGR growth over the next 10 years or so? I think you all have done a good job in this particular area by summarizing what's being offered. And sometimes I get this feedback that from a designer and architecture perspective, when they look at what's going on the advanced packaging side, they look at it as a maybe a word soup or something like that. There is a lot of different terminologies that are being thrown at customers, and there is a lot of different things that are named similarly, and a lot of similar things that are named differently as well. From my perspective, I think a good way to simplify the view on what's going on in advanced packaging is to look at the interconnect density. From my perspective, I think this is a good moral equivalent to what tended to be happening on the integrated circuit at the transistor level, right? So at the transistor level, people will refer to a specific node that represent the minimum feature at the gate widths or something like that from an integrated circuit perspective. The moral equivalent of that on the packaging side, from my opinion, is the interconnect density or the I/O density. And that reflects the bump pitch that you can offer from a packaging architecture perspective to support the increased density on the die. Now, if we take that view and look at what has been happening over time, you will see that there is a consistent trajectory of moving from a planar view where you can connect single or multiple die on the same substrate to a 2.5D where you can introduce an interposer or a bridge either directly or through an RDL on the substrates. And you can see what happens with info, for example, or the focus from AEC, the Intel and TSMC CoWoS and Foveros, and obviously the Intel EMIB that is a 2.5D into the substrate. The trajectory of that moving forward is continuing to reduce the bump pitch, increase the I/O density by transitioning into hybrid bond. So this is a direct metal-to-metal connection, and taking advantage of that by having a 3D stacking of different chips on top of each other. And in this particular area, TSMC with their SOIC, and whether it's the SOIC built on the CoWoS platform or the Info platform, tended to be the leading architecture in the market. Now, that's interesting to the point where we are in right now. But if you look at what needs to continue to happen in these scaling of different architectures, there are two distinctive approaches that people are taking. One approach is to continue the 2.5-3D scaling by scaling both the interposers and the substrate and making sure that the entire hierarchy is co-optimized so we are able to deliver the needed performance scaling at the system level. There is other approaches that says, okay, well, this is going to be complicated and we need to simplify that. So what if we get a different material that we can use to fabricate the substrate and the board, make them very flat, continue to have fine feature in them, and eliminate the interposer? That's an interesting approach, I think, but there is a lot of open questions and challenge that really put in question the realistic value of taking that particular approach. And the leading options for that is what people are talking about today by introducing a glass core substrate. So the idea there is if we can make a substrate out of glass, it will be very flat. And because it's very flat, then I can have very fine feature. And if I have fine feature, then I'm able to increase the density. And if I do that, then I don't necessarily need to have interposers and complicated 3D structures and all that. There is a lot of industry-wide reports on the validity of that approach, with a lot of open areas for further validation. Like, people really need to explain how vertical interconnects scalability through glass will continue to deliver what is needed, or how does the cost of that approach will fare against what's being offered today in the industry. One very important piece is thermal management and board level reliability. So that remains to be an open question. And obviously the whole thinking of, will glass be better fit as a thin interposer at the chiplet integration level, or will it continue to be introduced as a very thick material at the core level of the substrates? So hopefully that gives
Sam,
an idea.
I have a question on your previous slide. So
yes, this one?
Yes. So I think last week there was a seminar at INEMI by Intel on this topic. And the very last slide in that seminar was a call to action for the ecosystem to gather around glass, which basically tells me that a lot needs to happen for glass. So what is the reality of, from designers' point of view, how far along do you think it is before we should worry about it?
I see. No, so I actually think that there is a lot backed into this. So I think I attended the same seminar, and Intel was correct in calling upon the ecosystem to work together, because that actually is always the case that is required for packaging, for the reasons that I explained in the supply chain. The ecosystem does not exist here, right? So you need to have that communication, you need to broadcast what is needed, and you need to continue to collaborate with people, particularly in Japan, to make sure that a new technology is developed, or a current technology is continued to scale in the future. And if I look at the amount of work and the open questions that remains to be addressed in this particular offering, my guess is this is something that is probably 10 years away. And I think what was quoted by Intel in Semicon Japan, I believe, back in December, was that this is something they are working on toward the end of the decade, not something that is readily available today. So hopefully that answers your question, Joanne. I'm not sure if I addressed the point or.
So a decade is like an eternity, right? So.
Yeah, in this industry, there is a lot of things that needs to be addressed today with higher level of urgency, right? Yep.
Okay, thank you.
Sure. Okay, so hopefully so far I was able to give you guys a little bit of an insight into what's going on in advanced packaging and share my perspective. I want to summarize this section of the talk by taking a reflective look at what's being offered today from the leaders in this particular field and what is missing, right? So if you look at the roadmaps and the different architectures and the design rules that's being published and the directions that are highlighted to go in the future, there are certain things that are common. Most of these architecture are using what people refer to as a common mode material. It's silicon and an organic RDL. There is a singular focus on IO scale, right? So everybody's very focused on getting tighter dimensions so that the total number of IO per unit area is increasing, and hoping that will address the system level scale. Power delivery and thermal management tended to be something that gets done after the packaging material is designed and after the design rules are defined. Addressing this scaling out, or the large form factor and productivity and yield and design for manufacturing, is also a big challenge. Most of the advanced packaging options associated with the 2.5D and 3D requires a fab-like infrastructure, right? The exception to that is really EMAB, because EMAB is a passive pieces of silicon that gets done at a very cost-effective fashion in a fab environment that is not as advanced of a node. And then gets managed through the substrate manufacturing from that point on. So from that particular perspective, it's the only exception to what is being offered. Everything else, like a Fovaros or a CoWAS or an Info, required a fab-like infrastructure. And that actually gives us some insights into how fragmented the supply chain is. Right? So for an advanced packaging device to be coming about, you need fab contribution, you need a substrate, you need an interposer, you need an OSAT. And when you have that, co-optimization tended to be very difficult. And there is marginal stacking, and then there is inefficiency in the supply chains. What I think is missing moving forward is an optimized approach across this different interconnect hierarchy levels so that we are able to scale at a faster rate from a packaging perspective. What also is important is having a power delivery and a thermal management solution that are intrinsically built inside the advanced packaging. And I believe a way to do this would be through an innovation in materials and the manufacturing process. The last piece is, in order for us to be able to synchronize and co-optimize these different pieces of the supply chain, we need to simplify the manufacturing process from a packaging perspective. And we need to be able to do this either in a fab light or outside of the fab, or a fab independent environment that is more friendly to a packaging investment infrastructure. And the last point here is, it's really important that there is a big focus on building fabs to fabricate silicon and dies in a way that is more balanced throughout the global supply chain. You see there is a lot of momentum to do that here in the US, a lot of momentum to do this in Europe. So there will be a distribution of fab outputs that is not as concentrated in Asia. And that's a very good thing, I think. What needs to happen is a very similar focus to make sure that that's also happening on the substrate side and on the 2.5 and the 3D sides. And that's a very big lift, but it needs to start. So I think that concludes the first half of my discussion. If we have time, Jawad, I can quickly give some updates on what we're working on specifically from Hyperion. Would you like that, or should we stop here?
I think so. We have another 15 minutes. I think you can tell us for about 5 minutes and maybe leave the rest of the 10 minutes for Q&A.
Okay, no problem. Thank you. So what we are doing here in Hyperion is actually focusing mostly on addressing this missing items that I summarized in the previous slide. So maybe quickly I can show you what are the concepts we are working on and what's our fabrication approach, what we collected so far, and what is our thinking to address this supply chain and scalability concern moving forward. So we believe, as I explained, that coming up with an approach that addresses thermal management, power delivery, and continue to deliver I/O scaling is very important. We looked at this very carefully and we said, okay, if we are able to offer both material system innovation and manufacturing process innovation and combine those together so that we're able to address high frequency operation, power delivery, thermal management, and deliver fine feature inside this packaging with a cost-effective fashion, then probably we are able to address the main concerns in this particular industry. So we came up with two things. We came up with a process to pattern semiconductor-based interposers that we refer to as QCP, or quantum conversion patterning. It's a simplified interconnect fabrication technique. It's compatible with the back-end infrastructure, and it delivers the I/O scaling that everybody is asking for. But on top of that, we use this on a specific material that is not silicon-based and that is not organic-based. It's an inorganic wide bandgap material that is not necessarily a semiconductor grade, because we don't need to have that when we are talking about the packaging interposer. We are not creating an integrated circuit transistors inside. We are creating through holes and wires and fan out layers and stuff like that. So we are using our quantum conversion patterning in these particular class of materials because they have an intrinsic superiority when it comes to thermal conductivity, high breakdown voltage, and high frequency operation. And I will talk about some of the material properties that we are working with. And we used that process and that material system to construct the QCIA. This is our trademark architecture for 2.5D and 3D interposers, similar to the SOIC or the Foveros that are being offered in the market today, but built with our process and on this very specific material. So the concept is actually very simple, right? So if you look at what the industry is offering today with the Damascene process through an interposer, you get a piece of silicon that's typically 100 micron thin, and you create some very fine wiring, and you try to connect these wiring from the front end where the chips will be interfaced with to the back side of the interposer. The way you do that is either through a through silicon via or a bunch of stacked via, a bunch of staggered via, but the directionality of all these connections are only vertical, right? We looked at what if we are able to create these interconnect at omnidirectional fashion so that you are able to do that vertically, horizontally, at any angle, given the specific volume that we're dealing with. That will have a tremendous impact on increasing the interconnect density that you can offer in a given unit volume. So that's one.
Sam?
Yes?
Just a quick question, just so I get my bearings straight here. What you're trying to do is you're trying to offer a replacement for some kind of interposer, whether it's silicon, RDL interposer, or just RDL interconnect, or one of those million fan-out technologies that exist. What you're saying is that piece you're looking to do differently with your patent ideas. But the package substrate, that still exists, right? Where the interposer is typically mounted on the substrate, and that piece still stays the same.
Yeah, so I think that's a very good observation. So I think the short answer to your question is mostly yes. But what we are trying to do is really create this new way of fabricating the interconnect and then use it mostly as an interposer, but we can also use the same approach as the core of the substrate, right? So if you use it as an interposer, we are agnostic to the type of the substrate that you need to have underneath that, but we would have to have a substrate. We can continue to have the substrates that are being offered today or the new substrates that are being designed in the future, or we can introduce our technology to fabricate the substrate itself. But we would have to have a substrate, and that's correct.
Got it. Thank you.
Sure. The other key feature of the work we are doing is really simplifying the manufacturing process in a way that does not require us to volumetrically remove a material so that we can create a hole and then come back and plug it with a conductive and then do a CMP to planarize and then create the interconnect. We in situ convert the material that we're working on from a semi-insulating into a conductor, and we use that conductive phase to carry the current instead of copper. Now, you would say that in order for this to be successful, the conductivity levels, the resistivity, and the performance of that particular phase has to be equal or better than copper, and that's the case, right? Because we are using a silicon carbide-based material system, we use our patterning technology to convert that into graphene, and we use these graphene to create the vertical interconnect in lieu of the through silicon via that is available today. And that gives us the conductivity that we like, and also gives us the level of power delivery advantage that is not offered with just copper today. Now, to the question that was asked.
Time
yes.
check. So in 8 minutes, we have a hard stop.
Sure.
So you need to manage it. Give me like a couple minutes at the end to wrap up the meeting.
Yes, no problem. I'm actually going to be finishing here at this particular slide. I think to the question that was asked earlier, the traditional view is to have a chip sit on a package and then that package sits on the board. With our technology, we are introducing this QCIA and the QCP process to form an interconnect that can either be introduced right at the level of the chiplet reaggregation, so it can replace an interposer. We are also able to use the technology to create thermal management or thermal chips, and we are able to use that technology to create a power delivery and a thermal management devices as well. So you can introduce that at the interposer level. You can introduce this as very directed thermal management chip that gets integrated through the overall system, or we can also use that as a core of the substrate to replace the traditional FR4-like material if density and thermal management and power delivery are needed in that particular instance. That's not necessarily needed in all the cases, but in some cases that becomes very critical. And in these particular cases, we can use that to replace the traditional way of doing substrate. But nevertheless, our approach assumes that you will always need a substrate. And the reason for that is the fact that the gap between the package scaling and the IC scaling is too vast. We believe it's unrealistic to assume that you can just bridge it with an interposer alone or a substrate alone. So we designed our first test vehicles and we collected some data. We designed our second test vehicles, and this particular design for the second test vehicles really intended to house design rules that as tight as what you would need to route something like HBM3, for example, right? So we collected data as of how are we going to pattern that particular design requirement using our technology, and went down into the dimension of 1 micron, and from a vertical interconnect perspective, we went all the way from 50 down to 5 micron. I think middle of last year, we also published our organic substrate design rule kit in conjunction with the QCIA interposer. So we're targeting to have 100 micron thin interposer with 1 all the way up to 5 line and space. This omnidirectional via interconnect, our starting point is 10 micron with 20 micron pitch center to center. And the metallization depth or the thickness of this conductive phase that we are creating, we are taking it all the way from 5 micron to 1. So we believe that this combination of design rules, in addition to the advanced organic substrates that we design and use, will offer an attractive solutions for people that are designing into the AI and high performance computing. So I think, Jawad, maybe I can stop here, and thank you very much, everybody, for listening and for the great questions. I really appreciate it.
Okay, great, Sam. That was awesome. We have time for maybe 1 or 2 questions if anyone has.
Sam, so question from me, and this is Anu. What kind of time frame are you seeing on this, and you know, just estimating, looking into the future, where do you see this play out into the industry?
Yeah, thanks for the question. Anu. I think we have a very busy 2024 ahead of us because we need to take that particular design that we started working on and integrate it in an overall system. So the idea is by the end of this year, we have a functioning prototype at the system level with fully assembled chiplets. From a manufacturing point of view, we need to have the ability to produce this at a platform level that offers the economy of scale. So at this point, we are offering all our prototypes through a wafer-based infrastructure. The wafer-based infrastructure is great to demonstrate capability, but we have plans to take that and use a hybrid process that combines both wafer platforms and panel platform in order for us to achieve the economy of scale. We identified all the different manufacturing flow and the equipment that needs to do that, and we're working on securing the investment that can get us there. Now, that takes time. I think it will probably be at least 2 or 2.5 years in order for us to have that infrastructure in place and be able to start producing and continue the technology development. But in the meantime, we have a FedEx flow that we are able to use across our ecosystem partners from an equipment and materials perspective that we can continue to use that to deliver prototypes and designs.
Well, thank you. It's very interesting, and I really appreciate your time, Sam.
Thank you so very much. I appreciate the question. Really appreciate it.
Same quick question. This James here. Sorry, I didn't even get just about the cost and also performance, right? How you compare to existing solution.
Yeah, no, that's a good question, James. So I think cost perspective, we compare ourselves to silicon interposer. And if you look at the cost and the margin stacking associated with silicon interposer-based offering today, they are extremely high. We believe that relatively, when you compare us head-to-head in terms of the infrastructure that we use to produce this and the simplicity of the process, that as we are today with a very limited volume, we are coming at parity or lower. We believe that with the roadmap that we have and the economy of scale that needs to be built around this, we will be at a much more cost-effective compared to silicon interposer, for sure.
Got it. Appreciate it. Thank you.
Okay, great. I think we are pretty much out of time. Thank you so much, Sam, for taking the time this morning, and really appreciate that. We'll pretty much wrap up this meeting. Next week, we'll have a little bit of organizational discussion, and hopefully that would be the first meeting where Anu basically runs the meeting. So we should all welcome Anu as the new co-lead of ODSA. So looking forward to that, Anu.
Thank you, Jawad.
Okay. So with that, we just wrap up today's meeting. Thank you, everybody.
Thank you.
Thanks. Bye.
Right. Thank you. Bye.